Welcome to the lair of the Batty Boffin.
Hi there Batty fans, and welcome to another Batty Boffin video all about electricity. In this video we're going to be looking at the differences between series and parallel wiring circuits. You might have heard these phrases on earlier videos. Here we've got two circuits. This one we've got things arranged in series, meaning they follow around one after another. Here we've got three things arranged in parallel so that they look like the rungs of a ladder. I've got these marked as resistors to 1, 2 and 3, but they could be anything. They could be light bulbs or something like that. And in each case they've got switches next to them as well. So the first question is, let's say we had things wired up like this. At the moment the switches are all open. But what happens if I closed one of them? That means I shut it so the electricity can flow. What would happen if I closed one of the switches there? Well, absolutely nothing. If I close one of these switches, the electricity can flow through there, but it can't get through there. So nothing happens. So this actually would be a pretty pants way of wiring things up. Imagine if your house was wired up like that. You close the switch, as in switch on, the switch for a light, and nothing happens. And then what you'd have to do is go around the house and switch on every single switch, and then everything in your house would come on. That would be a pretty daft way of doing it. To be honest, we don't use series that much. I'll tell you one place we do use it later on. We much more often use parallel. So have a look at this one here. In here the wire comes down, the main circuit splits off into several different rungs of a ladder, and each one has its own switch. So again, tell me what would happen if I closed one switch. Well, the answer is the electricity would flow through this one. So if that were a light, that light would come on and all the others would stay off. And that's what we want. In a car, you want to be able to switch on the right indicator light without switching on the headlights, the fog lights, the rear wheel heater and everything else as well. So we tend to wire things up in parallel for this reason, because the switches then individually control things. There is one place where we use series though, and that's in Christmas lights. The little fairy lights, you know, they tend to be wired up in series. And we know this because if one bulb blows, that's the equivalent of opening a switch and the whole string of fairy lights goes out. And I don't know if you're anything like me, you've had that experience on Christmas Eve of sitting there trying to find out which bulb's gone. Most annoying. That's because they're wired in series. But there is a reason for that, which we're going to discuss on the next board. So pause for a minute while I wipe down this board. Well, I'm going to wipe out part of the board and put some things on. And we're going to come back and discuss amps and volts and resistance in series and in parallel. Back in a minute. Right, here's some more bits about series and parallel currents. I've kept the circuits the same, except this time I've replaced all the switches by ammeters, and I've added a voltmeter over each component. So it does look a bit complex, but it's nothing too bad. We just have an ammeter and then our resistor, ammeter 2 and resistor 2, ammeter 3 and resistor 3, and a total ammeter. And then over each component there's also a voltmeter and a voltmeter in total. Here again, the total voltmeter, a voltmeter for resistance 1 and an ammeter for it, resistance 2, voltage 2 and ammeter 2, resistor 3, voltmeter 3 and ammeter 3, and a total one. Okay? Obviously in a circuit you wouldn't normally have this many ammeters and voltmeters, but we're just going to look at how the things combine. Now, if you've seen some of the earlier videos, you may know something about this. Like in some of them, the voltage is shared between the components and the amps stay the same. And in other one, the current is shared between the components and the volts stay the same. So, on the basis that you may know a little bit about this, I'd like you to pause the video and see if you can fill in any of these. So if you think that the voltage in total is the same as all the other volts, you'd put V total equals V1 equals V2 equals V3. However, if you think that the voltage is shared out between them, then you'd put voltage total equals voltage 1 plus voltage 2 plus voltage 3. So you have to add the three individual voltages together to make the total. Okay? So have a go with those, see what you can do. If it doesn't mean anything to you, don't worry about it, because I'm going to go through it afterwards. See you in a minute. Welcome back. In a series circuit, the amps are the same all the way round. So the ammeter total is equal to ammeter 1, which is equal to ammeter 2, which is equal to the reading on ammeter 3. The amps are the same all the way round, but the voltages get shared out. So voltmeter 1 plus voltmeter 2 plus the reading on voltmeter 3, when you add them up, make the total volts. We did one where we had some resistances that were all the same, and we found with a 6-volt battery we got 2 volts, 2 volts and 2 volts. Or if the resistances are different, you might get 3 volts, 2 volts and 1 volt, but they all always have to add up to 6. The resistances also just add up in a series. So resistance total is equal to resistance 1 plus resistance 2 plus resistance 3. So you simply add them up. If that were 10 ohms, 10 ohms and 20 ohms, then you'd regard that as one single 40 ohm resistor. Nice and easy. Okay? The voltage is shared out and the amps, the voltage is shared out, the amps are the same all the way through. It's the opposite way round in parallel. In parallel, the volts that are coming down here are all the same through here. So all the voltages will read the same. Voltmeter 1 will be the same as voltmeter 2, will be the same as voltmeter 3. And that'll be the same as the voltmeter total, they're all the same. However, the current gets shared out. So AT, the total ammeter, you need to add those 3 ammeters up. So ammeter 1 plus ammeter 2 plus ammeter 3. Add up to make the ammeter total. Resistance is a tad more tricky. There'll be another video on how to do this one here. It's not quite the same as that. It's very nearly the same as that. But instead of adding up the resistances, you add up their reciprocals. Reciprocal's a posh word for upside down fraction. Don't worry about that too much. There's going to be a video on how to do that. That's slightly complex, adding up, which is one of these reasons we looked at some of the earlier videos, that whatever these resistances are, if say like that's 10 and that's 20 and that's 40, here if it was 10 and 20 and 40, those would add up to 70. 10 plus 20 plus 40 on these actually add up to something about like 5. It's very small. They actually get smaller when you add them on these because you're adding the fractions, but as I say, we'll do that in another video. So these are important. The big ones are in series. You share out the volts, but the amps are always the same. In parallel, you share out the amps and the volts are always the same. Okay? So we'll do some of that in the next video and I'll see you then, Batty fans.
Mwahaha! Mwahaha! Mwahaha!